Hello. This is week number 9, CHEN 121, March 22nd, 2021. All right, so today we'll be talking about, again, data fitting and regression in Python. So if you recall, last week we did some linear fits in Python using the data for the concentration versus time. We generated the straight line equations for a bunch of different variations. What we're going to do this week is now we're going to determine the R squared values for these linear fits, right? So what's the logic of doing this, or why am I doing this? What's the point? Let's have a look at what R squared is, right? And this will really make you understand. So anyways, R squared is the coefficient of determination, and basically it's a metric to gauge the effectiveness of a linear fit to a set of data, right? So if you recall from last week, let me go to Spider. So this is last week's code. If I run it, if you recall, we had 4 different plots, right? We had 4 different plots. Actually, it's this one. Let me close this guy out. Let me run it. Right, so we had 4 different ones: CA, CA squared, ln CA, and 1 over CA. And as you can see, some of them did not fit a straight line very well, or not at all, actually. Some of them fit a straight line very well. Usually, as engineers, we don't like to say, oh, it doesn't look so good. We want a numerical metric, right? And this is what R squared does. This is what this R squared parameter does, well, achieves basically, right? So R squared is called the coefficient of determination. And what this parameter basically does, it tells you how good the linear fit is. And the equation value for R squared is, the sum of all your, these are called residuals, over the sum of all your differences, right? So it's 1 minus yi minus yi at this point. So this is the difference between every point and its corresponding point on the line. And this is the difference between every point and the average value of all the points. And by doing this calculation statistical parameter, you'll get an R squared value between 0 and 1. And again, yi is the experimental values for y. Yi dot hat, or chapeau, whatever you call it, is the predicted values of y, and y dash is the average value of experimental y values, right? So this is all your average values. If you have measured, let's say, 10 parameters, you average them all, you get your average. Calculate the difference from every point to the average, and the difference from every point to the point predicted by the line. You add these two lists up and divide them by each other. 1 minus, you get an R squared value. Basically, R squared is a measure of what percent of the prediction error is eliminated when applying the linear model. Okay, usually it's called the goodness of fit measure for linear regression, right? So if R squared is 1, then it's a perfect fit. If R squared is 0, it's maybe not a good idea to use this fit. Okay, and R squared is always between 0 and 100, or between 0 and 1, right? 0% represents a model that does not explain any of the variation in the response variable around its mean. Basically means that this line has nothing to do with this data. It's just predicting something way off all the time. 100% means that the model represents all of the variation in the response data. So basically, if you get an R squared value of 1, means that this line or this equation perfectly matches your data. It's a good correlation to use. This is something for you later on in life. So, as you progress throughout your careers, this is a 101 course or 121 course. So, when you're in the 400 courses, I don't know, you're in your career, be careful. R squared, use them with caution to complement your judgment, right? Don't use R squared for nonlinear fits. People tend to do this a lot. So they have a logarithmic fit and they use R squared. It's not a good idea, right? Because it's not going to work once you extrapolate or go outside the list. And if you're using R squared for nonlinear fits, make sure to put the range of this R squared value. So let's say I have a polynomial fitting a curve, and the polynomial fits this curve perfectly, and you say R squared is 1. Just make sure this R squared is equal to 1 between x equals 0 to x equals 10, whatever you fit this polynomial on. Because a polynomial will go up and down, right? So if I go look at x equals 20, which is outside the range, polynomial zips to a negative, your estimation is completely wrong, right? So with nonlinear fits, be very careful when using R squared as a blanket judgment on the effectiveness of your correlation or of your fit. Okay. Okay, so how do we get the R squared in Python? We're going to use this command here, scipy.stats.linregress xy in Python. This is really the command you use to get your R squared value. And we can really use this command to create, to get the slope and intercept, but we're not going to do that. We're going to use our curve fit command like last week, because curve fit makes it easier to expand to other function form. Lin regress, you can see lin is linear regression, so you can use this. It's only valid for straight lines. What this function does, it calculates a linear least square regression of two sets of measurements, right? First set will be your experimental data. Second set will be your line. It takes two parameters, x and y, right? They both have to be array-like, so they have to be arrays, have to be lists. It cannot be one value. It'll just calculate basically an error, or so it'll give you an error. Whatever it is, you need two sets of measurements. Both arrays should have the same length, right? If only x is given and y equals 1, must be two-dimensional array. And this is copied really from the loop, from the Python manual. You can go and read it by yourself if you want to, but basically I need to give it an x and a y for it to calculate the linear regression. And it returns 6 things, and this is what they are called, right? Called slope. It will return a slope, which is the slope of the regression line. It will return an intercept, right? And this is what they're called: slope, intercept. Intercept is the intercept of the regression line, and it returns them in this order, right? It will return an R value. R value is your correlation coefficient, which turn a P value. P value is your, it's something called the p-value. It's a statistical parameter. If you end up going into life sciences, or doing research in life sciences or medical type research, they love to use this p-value as their statistical parameters. Engineers, we don't, chemical engineers specifically, we don't use it a lot, but it's good to learn it if you end up maybe in systems engineering or something. You can read up on it. Standard error is a standard error. Intercept standard error is a standard error of the intercept, right? And the first one is just standard error of the slope. So what we're going to do this lab is we're going to look at last week's lab, and we're going to calculate R squared. So if you remember last week, I told you plot them and give me your comments, give me your thoughts, and you did that visually. You looked at the lines. Oh, this line fits very well. It matches the data. This line does not. So what we're going to do this week, we're going to calculate R squared, so we have a numerical basis, right? We have a proper numerical judgment for our comments or for our thoughts about these plots. So what we're going to do is, again, our data, right? T, CA, you have time, concentration, and what I want you to do this week is, using last week's script, determine the R squared values for the 4 following correlations. So basically, we're going to open the script we wrote last week, and then we're going to add this command, which is scipy stats linregress, to determine the R squared value for each of the 4 straight lines we got last week, and report the results of the linear correlation and comment on the results. Okay, so let's go to Python and let's have a look on how we want to do that. Okay, this is last week's script. Now let's go over it. let's go over it and see where exactly we want to add these lines or this line to create the linear regression. Okay, so this is the code from last week. Was it week 7? Yeah, this is the one. I think I just have the week number wrong. Anyways, call it week 8. Doesn't matter. Okay, and now I'm gonna make this modification for the linear regression or to get this parameter. And if you recall, I'm gonna zoom out for a second. If you recall the structure of last week's code, we had our input lists, which were temperature and concentration. Then we had a for loop to generate the 3 other lists, which are CA squared, ln CA, and 1 over CA. Once I had these 4 lists, we wrote the robust code where we defined the objective for the straight line AX plus B. We defined the X and Y parameters, temperature and concentration, time, and concentration for this case. Then we had time and ln CA, time on 1 over CA, and time and CA squared, right? And then we used the curve fit function to populate the slope and the intercept. And we said the curve fit takes 2 parameters, objective, which is the handle for this function form, X and Y. And then I generated the 2 lines, the straight line and the experimental data. So now what I'm going to do is at the end of each, and I have 4 blocks, right? I have CA versus T, my first block, CA squared versus T, second block, ln CA versus T, third block, and 1 over CA versus T as my 4th block. What I'm going to do is at the end of every block, I'm going to add a couple of lines to determine the R squared value. And the way, as we said, this, let's go back to the Word file or the lab for a second. Give me a second, let me find it. Okay, let's let's go back to the Word file. As you can see, we're going to use this command scipy stats linregress xy. And this command basically returns a bunch of different values. So you have to be careful when writing this command because we will always want to specify, 5 or 6 outputs for it to work properly. Okay, so let's go to Python and see how we're going to do this. So I'm going to specify the outputs as they were listed. So we said slope, we said intercept. Let me zoom in. Maybe this is even better. Said slope, we said intercept, we said R value, we said P value. These are the outputs this function will give you. Standard error, and with standard error it will return 2 of them, so you can put the intercept standard error as well if you want to, but it doesn't matter, so I'm just going to keep it as 1. Say ln regress X data comma Y data, right? And this is really the only line we need. Afterwards, I'm going to calculate the R squared. I'm going to call it R, let's call it R squared, and this will be the R value which was returned to the power 2. So something I didn't say before, ln regress will actually return the R value, which is just the square root of R squared. So I'm just going to square it to get the R squared value, right? The R value in itself has its own statistical relevance. So if you're doing some advanced statistics, doing data analysis, you become a data scientist, this or that, you might be interested in this R squared parameter. But for this R parameter by itself, but for our purposes, we're just going to use R squared, and then let's print out the results. So I'm going to say print the R squared value of this linear fit is, and I'll just plot the R squared number right next to it. Good. So these 3 lines should really, you can see I did a test run before. Well, basically you should see the correlation, you should see the R squared value for each of the linear fits. Let's try it by ourselves here for a fresh start. Let's run it and see if it's going to run. So it's not happy about something. It's saying name linear regress is not defined. Okay, and when you get this type of error, linear regress is not defined, it basically means you didn't call it at the top. So you need to go to the very top, and this type of error is common. You know, sometimes you're switching between scripts, whatever it is, and you forget to import the right library. So what we're gonna do here, again, I'm gonna write from scipy dot stats import lin regress, right? So again, I'm just importing scipy.stats and importing lin regress. An alternative form, so if you don't want to just write from import this, alternative form to these two would be to just say import scipy, right? You can say import scipy, and then at the bottom when calling a scipy subfunction, you need to put scipy dot linear regress. You can do it this way, and it will work similar to when we're doing if you recall, we're taking a natural logarithm. I think we have it at the bottom, or actually have it at the top here. When we were taking the natural logarithm of lin, we had to call np.log I, right? I had to call the main library first and then the subfunction. For our cases, I don't want to do this. I'm just calling the function itself at the top. So what I'm doing is I'm just calling linear regress at the top by itself from scipy.stats import lin regress. Okay. And this allows me to use lin regress directly without using scipy.lin regress. Okay. Just makes it easier with these types of functions, because sometimes you have a typo here, you do this or that. It just makes it easy, straightforward to troubleshoot. Anyways, so once I add this line, it should run fine. So let's go back to the point here. Let's try to run it, and hopefully it runs fine and we get the R squared value. Give it a try. It's still not happy. Why is it not happy? Slope, intercept, R value, P value, standard error, then regress, X data, Y data. Oh, okay. In our case, the X data and the Y data should be X and Y, right? It should be just X and Y. X and Y, because I wanted to linear regress my experimental data, right? My T and my CA squared. So let's try it now. Good. So I have my correlation for CA, my correlation for CA squared. The R squared value for this linear fit is this. So I get the R squared value for the CA squared. I'm getting 0.813. So now we have this function form working. Now let's put it as part of our code for all four of them. So I'm going to CA versus T at the top here. I'm going to put this at the end, just paste it. We already did it for CA squared. I'm going to lin CA versus T. I'm going to paste it here at the end. And then 1 over CA versus T, I'm going to paste it here at the end as well. And this is really the function form, or basically the, what do you call it, the syntax to achieve this, to get the R squared value for these plots. If I run it now, I should get 8 lines, right? Correlation is this, R squared value is this. Let me copy and paste these results here so that you can see them clearly. So I'm just pasting them here at the end. This is really what you're gonna get. The correlation is CA, have a number multiplied by T. R squared value for this linear fit is 0.907. CA squared, R squared value is 0.81. Lin CA, 0.97. 1 over CA is 0.999. Basically, 1 over CA is the best fit, as you can see here, or as you can see in your figures, 1 over CA is the absolute best fit, has R squared of almost 1, basically 1 really. Lin CA is the second best one, 0.97. It's okay, it fits the curve reasonably well, but there are points which are overestimated, points which are underestimated here. CA squared, this is really the worst fit, 0.81, really bad, you know, it doesn't really catch anything. And CA versus time, it's also a bad fit, you know, 0.907, because these cancel out, but on the overall, it's not a good fit, okay? And here, using these numbers, you can really gauge how good of a fit you have numerically, right? So now you can tell me 1 over CA is the best fit because R squared is 1, it's higher than the rest of these guys. This is the fit we should use when we're presenting this data, right? You have a numerical metric you can back your claims with. Okay, so this is the end of this lecture. Again, a bit of a short lecture, but make sure you understand the idea of R squared. Make sure you understand the functional form of linear regress and how to use it. This is really the main takeaway, right? Linear regress, the functional form of it, how to use it, how to gauge different sets of data, how to understand how they behave, etc. As part of your homework for this week, you have to get to the R squared for the other 2 data sets which we're dealing with, right? So please do that. Please, office hours are from 5 to 7. This week is a bit of a short lecture, so if you're falling behind on any of the previous submissions, you're falling behind on understanding anything, please come to office hours. This is the week to fix it, right? This is very important. Make sure you're on track. Make sure you're not falling behind. If 5 to 7 every day does not work for you, send me an email. We can talk earlier in the day. We can talk on Saturday. We will make things work out so that everyone's on track, okay? What other thing? Also, feel free to send me an email if you want an extension or you're having some issues. Just send me an email. I can always reply. Submissions are typically due every Monday before the lecture, right? Every Monday before 11 a.m. Please make sure to have all of your submissions from the previous week into Blackboard or email to me if you're having some issues with Blackboard. All right, so thank you very much, and I'll talk to you guys next week.